There's a lot. I'm not officially enrolled in this.
Are you auditing?
I was like, basically, I should go to like this number or but you need to put it on. I was missing that.
So what do you think the ideal is like if your predictions are biased? And then yeah, if your predictions are biased, you just subtract away the bias in your prior score. And the prior score.
I doubt.
So a lot of this means that like your optimal prior solution should never be biased. See, this is more biased.
Biased. It's like positive. Basically, functional like analyzing inference for like those like
If you're so
like R squared. When you do regression,
Are like the relation very exactly.
okay, like how you derive
They're very.
we haven't done it. Like, I think how you
They're not doing it appropriate. Several weeks.
like why these models like yeah, like what's your those things like the R squared.
Okay, so welcome back. Before I begin, any administrative questions about the class? My plan is to remind you of what we did last time and then just like charge ahead if nobody asks any questions. It's typically a good time for folks to like raise their hand if they're badly confused about either course content or comments or anything like that. Any administrative questions before we begin? Okay. So just to remind you of what we did last time, other than setting up sort of basic notation and stuff, we defined sort of the bare minimum consistency condition that we might ask from a model. When I say consistency, I mean consistency with respect to some underlying distribution. And in particular, last time we were talking about sort of real valued regression models that are trying to predict the mean of some one-dimensional real valued label. Okay, and we sort of talked about this sort of idealized but unobtainable goal that what we really want these models to do is, given features X, try to predict the mean of the conditional label distribution given X. Okay, and so that's like the idealized goal, that given X, we somehow, know everything there is to know about the label distribution given X for this particular X, and we predict the mean of this label distribution conditional on X. Okay, and we sort of argued that actually, like, even though this is what we want, it's sort of going to be fundamentally impossible. We gave a simple example. It's going to be fundamentally impossible not only to like do this, but even to really know if we've succeeded, because we wrote down two distributions that are observationally equivalent. We can't distinguish them just from samples from these distributions that have conditional label expectations that are sort of as different as possible. Okay, and so the approach we started taking is to say, okay, well, I can't even test for this condition that I really want, which is that my predictions should be correct conditionally on the feature vector X. Why don't I start asking for sort of much weaker conditions? And we started with an extremely weak one, which was just what we called marginal mean consistency. It's really just the same thing as statistical bias. That asked that our model predict on average, if we average over all of the examples, if we take the expectation over the distribution, make a prediction that on average is correct in the sense that it is equal to the average, again, marginalized over all of the examples, the label. Okay, like if we were truly predicting, the true conditional expectation given the features, or like maybe the universe isn't random at all and we're making perfect predictions of the label every day, we would of course satisfy this condition. And so if we ever see a model that doesn't satisfy this very simple condition, it must be wrong, right? It must not be the model we're looking for. But of course, it's possible to satisfy this condition without knowing the true conditional quantities. Like in particular, example we gave in which we've got two observationally indistinguishable distributions. that have very different conditional label distributions, well, of course, they agree marginally on what the average value of the label is, averaged over examples. If they didn't, they would be distinguishable. Okay. And so we asked for marginal mean consistency, and then we defined this loss function, which you'll recognize as squared error, and sometimes we called it Breyer score. And we showed that it had this very convenient property with respect to this goal we had sort of set out, which was getting the label mean correct on average. Okay, and we proved the following lemma. We said, look, we've got any model F mapping features to a number that is purportedly the conditional label expectation, conditional on the features, and maybe it's got some statistical bias. Then we let delta be exactly that statistical bias. Delta is the expectation over the underlying distribution of the label minus the expectation for the underlying distribution of the prediction of the model. If we had no statistical bias, this would be 0. Let's say our model does have statistical bias, and so we correct it by just sort of shifting the model by delta. Okay, so we have this corrected model, which we called f hat. F hat is just f of x uniformly shifted by delta. So we just added a constant to every prediction of the model, exactly so that this shift is exactly removing the statistical bias. And what we showed is that if we look at the Breyer score of f hat under the underlying distribution, and if you remember, this is just the expected squared error of the model. Okay, so the thing you would optimize for if you were solving like a standard squared error regression kind of problem. This was going to be exactly the squared error, the Breyer score of the original model, less by exactly delta squared. This wasn't an inequality, this was inequality by sort of correcting this bias. If you discovered it, you would reduce the squared error by exactly the square of the shift that was necessary to debias the model. Okay, this was one of the reasons why we sort of liked squared error as a loss function, as a scoring rule, if the thing we cared about was means. Okay, and one sort of simple corollary we noted about this, which is sometimes referred to as the fact that squared error elicits means. You know, if I were just solving a squared error regression problem over some distribution, and the class of functions that I was optimizing over was just constant predictors, things that predicted for the same example, the same number. Okay. Then this is saying, well, what I would find minimize squared error over any distribution was just the mean of the marginal label distribution, right? Like one convoluted way of computing the mean of some distribution would be to solve this squared error regression problem rather than, just averaging over a bunch of examples. Okay, so the sort of way this is sometimes said is that squared error elicits means of a distribution. And there are other properties of distributions, and you can ask the question, are there loss functions that elicit those distributional properties? And if so, what are they? You can ask it the other way around as well. If you write down any loss function, it elicits definitionally some property of a distribution, whatever the functional form of the minimizer is. Okay. That was sort of like a quick summary of maybe the punchline at the end of last class. But make a rough amount of sense. Okay. So means means are a very interesting distributional property, and we'll probably spend at least half the class talking about predictors that are trying to predict things that are related to means, the averages of things. But sort of the sort of maybe second most useful distributional property for us in this class are going to be quantiles. So quantiles come up a lot when you're trying to sort of think about robustness or risk aversion, right? Like means can be, means are very sensitive to outliers. Whereas if I want to do something like, say I'm in some kind of high stakes decision-making setting, maybe I'm like a self-driving car, I want to like avoid killing people. Quantiles let us talk about not the average value of our risk, but sort of tail risk, right? Sort of, I might be interested in the 99th percentile quantile of my risk. What is the, what's the worst things can get in all but sort of the 1% worst case, right? That's what quantiles talk about. And when we talk about prediction sets, in particular conformal prediction, it's going to be all about quantiles. Okay, so what I want to do sort of in the first part of this class is to repeat a little bit what we did last class for means, but for quantiles. Okay, so first of all, I want to tell you what a quantile is. Second of all, I want to give you what is called, basically a proper scoring rule for quantiles, a loss function that elicits quantiles in the same way that squared error elicits means. And the fact that there's sort of this, this is something that'll come up as the course goes on, the fact that there's sort of this symmetry between means and quantiles, sort of, I'm going to define this thing called pinball loss, and essentially means are to squared error as quantiles are to pinball loss. What we're going to see is over and over again, everything that we can do for means, we can also do for quantiles. We can give the same kinds of conditional guarantees that we're going to unfold over the course of this class. Generally, for any elicitable property where the sort of potential functions that drive our arguments will be the proper scoring rules that elicit those properties. Okay, so quantiles are elicitable just as means are. Okay, cool. So let's talk about quantiles. So everyone probably knows what like the median of a distribution is. Or actually, like, it can get a little bit fiddly to define if the distribution is not continuous. And so I'm going to pretend throughout this course, just for simplicity, that all of the distributions we're working with are continuous, which is going to make all of our definitions and arguments a lot nicer. Everything that we do, you could also do it for sort of distributions with point masses. It would just lead to uglier notation. And one thing I want to sort of remark on is that if you're bothered by this, you can always enforce the condition that a distribution is continuous by just sort of perturbing it by very, very small amounts of noise from any continuous distribution, a Gaussian distribution. Okay, so to the extent, either you can sort of imagine that it's present in the world already, that's because of measurement error, or if you're like super bothered by it, you can like add small amounts of Gaussian noise yourself, and then this simplifying assumption of continuity will come to pass. Okay. So assuming that our distributions are continuous and thus wishing away some annoying corner cases, what is a quantile? Well, let's fix any Q that ranges between 0 and 1. Let's say that tau, some real number, is a Q quantile of some one-dimensional label distribution if probability, when I sample a label from this label distribution, that it falls below my threshold tau is Q. And if we want to sort of refer to the inverse of this function, I'll sometimes write that the quantile Q of tau equals little q. Okay, so it's, like this is a generalization of the median. The median is a 50th percentile quantile. The median is sort of a number such that exactly half of the distribution lies below the median and half of it lies above the median. But I can talk about quantiles at levels other than 0.5, right? I could talk about the 90th percentile quantile. That would be some threshold such that 90% of the distribution lies below it and 10% lies above it. Okay, why are quantiles interesting? Well, all sorts of reasons, but to the extent that you're interested in sort of risk-averse decision making, you might be sort of curious about what sort of your tail risk is for different actions you could take, right? Tail risk is just another way of saying, essentially quantiles of your loss or your risk distribution, right? Like maybe I'm interested in how bad things can get in sort of all but the 1% of worst cases, right? Like maybe if I'm sort of optimizing for my expected utility, maybe I think that, to the extent that the atmosphere lights on fire, my utility is going to be like super negative. And so, maybe my expected utility is always extremely negative. This might make decision making difficult. But if I sort of worry about it, if I think that that's really a tail risk, something that's not going to happen in the 99% best cases, best case outcomes, then maybe it's sort of easier for me to think about how to optimize my sort of decisions. Okay, is it sort of clear what quantiles are? Okay. So if we're interested in quantiles, just as we sort of thought about the idealized predictor that we would want to get our hands on in the case when we were predicting means, if we're interested in quantiles, there is some idealized predictor that is just as hard to get our hands on, which, given any feature vector x, predicts some target Q quantile of the label distribution conditional on x. Okay, for exactly the same reason as it was sort of impossible in the worst case to sort of get our hands on this true conditional predictor for means, it's just as impossible to get our hands on it for quantiles, because again, you can define two distributions that are indistinguishable from samples because they are identical except in when they flip their coins. Okay, so we can't do that, but we can go through the same exercise that we did for means. We can start by defining minimal consistency conditions, sort of the equivalent of statistical bias, but quantiles, and falsify models that do not satisfy those. If you give me a model and it purports to predict true conditional quantiles of the label distribution, and yet it fails, simple sanity checks, that fails to satisfy what we're going to call marginal quantile consistency, then, I know you haven't found the right model. Make sense? Okay. So by analogy to marginal mean consistency error, we'll say that a model, again, a model F mapping features to numbers, let's say that the label distributions we're thinking about without loss of generality are scaled to lie on the range 0 to 1, so that we can think of our quantile predictors as also lying in that range. A model has marginal quantile consistency error alpha with respect to a target quantile Q So there's many quantiles, so now I need to tell you which one I care about with respect to a target quantile Q. If when I look at the probability under the label distribution, under the full data distribution, that the predictions that I make for what the Qth quantile, what the sort of Qth quantile are conditional on X. So when I look at the frequency with which the predictions that I make for the Qth quantile exceed the label, well, you know, if I was truly predicting the median, the true conditional median of the label distribution, my predictions would exceed the median 50% of the time. If I was truly predicting, you know, the top 10% of the distribution, my predictions would exceed my predicted threshold 10% of the time. And more generally, what I should check for as a basic marginal sanity check aimed at falsifying whether I'm actually predicting a Qth quantile is whether, on average, over the whole distribution, my predictions exceed the label a Q fraction of the time. And if they don't, the extent to which I deviate from this, the extent to which I over or undercover the label above or below my target of Q, I'll call that alpha, my quantile, my marginal quantile consistency error. Okay, does this make sense? This is sort of the quantile analog of statistical bias of what we call marginal mean consistency error. If we did have a true conditional quantile predictor, it would have you know, alpha equals 0, right? If we were predicting the median, the true conditional median of the label distribution, the realized label would exceed our prediction, well, 50% of the time conditional on the features, and therefore also 50% of the time marginalized over the features, which is what we're measuring here. And if I don't cover the label 50% of the time as marginalized over the features, I must not be predicting the true conditional label probability. Does that make sense? Cool. Okay. And so, you know, in some sense, like, it's less interesting falsifying a model if there's nothing we can do about it, right? Like, the nice thing about statistical bias, marginal mean consistency error, that we noted last time is that, you know, look, if you give me a model and you tell me it's predicting the true conditional means, and I compute its statistical bias, and I find actually no, it's got statistical bias delta, it's not computing the true conditional means. It's not that all I can do is, you know, say, haha, you suck, like your model's wrong. Like, there was this extremely simple thing I could do. I could just shift your model so that it no longer had statistical bias. And, you know, to the extent that you cared about squared error, you shouldn't be mad at me for doing that, right? Like, that shift would improve your model as measured by squared error. Okay, so it's sort of like a win-win there. To the extent that I could falsify your model in this way, I could also improve it. Okay, and so that's the kind of thing that we want to find here. By the way, like, maybe just as a hint for like where we're going philosophically, right? It's sort of important, and it'll come up again, that our ability to falsify a model with some class of tests also tells us directly how to improve the model. Okay, suppose we've got a class of tests that is, you know, large. Well, maybe it's like hard to imagine tests that don't fall into this class. And I have the property that, to the extent that I can falsify the model with a test in this class, that gives me a certificate that directly allows me to improve it, say by shifting the predictions in some way. Okay. Now, maybe it's computationally or statistically hard necessarily, potentially to like apply all of these tests simultaneously to some model. Still means that anytime I can find any evidence that your model is wrong, I can fix it. So what does that sort of imply at convergence? It implies that, very quickly, we will get to a point where the model is, well, maybe perfect. Maybe you did find the true model. But if it's not perfect, at least nobody can tell. Right? It's sort of, like indistinguishable from perfect. Because if someone could tell, the very fact that they could tell would give us a way to improve it. Okay, and so that's kind of what we're going to be looking for. And in particular, like to the extent that these models, we want them to be useful for stuff, useful for, say, downstream decision making. If the real model, if only we could get our hands on it, would be useful in some way, but the one that we have right now is not, well, that's one way to falsify that we don't have the real model. Okay, so to the extent, we're doing very simple things now, but like, I think maybe it's useful to understand this guiding principle that we're after, that we want that to the extent that, there are data and sort of computationally efficient ways to falsify models, things like checks of marginal consistency with respect to various statistics. It would be really nice if the fact that we failed that check gave us a direct way to improve the model. Then we'd have sort of this virtuous cycle that would sort of necessarily get us to a point where, even if we can't hope for guaranteed perfection, we have these very simple counterexamples, we're guaranteed to get to a point where nobody can tell. That makes sense? Okay. So let me now define for you a pinball loss. This is going to be, you should think of this as the analog of squared loss, but for quantiles. So pinball loss, pinball loss function for target quantile Q is defined as follows. I'll write this as LQ. It's the loss. There's many quantiles, and so for each of them, there's a different loss function parameterized by Q. It's a function of tau, the predicted quantile, and y, the realized label. It's just a piecewise linear function. If the label is bigger than the predicted quantile, then it's just y minus tau times q. Okay, it's just a linear function with slope negative q as a function of the predicted quantile. On the other hand, if the loss, if the predicted quantile is larger than the label, then this is just tau minus y instead of y minus tau times 1 minus q. Okay, in that case, it's a linear function with slope 1 minus q. And this is how I evaluate the loss function given a realized label y. But if I'm given a distribution, given a data distribution, D and some model pinball loss I want to evaluate, some model F. I'll say that the pinball loss at quantile Q of model F on distribution D, well, it's just the expectation of this loss function on examples drawn from D. So what is this thing? Why is it called pinball loss? Like one thing you might note when you like stare at this thing is that this is some generalization, some parametric generalization of just the absolute value function. Okay, so like when Q is 1/2, when we're using quantiles to really just talk about the median, this function is just 1/2 of the absolute value of y minus tau. Okay, so for example, if Q equals 1/2, then a simpler way to write this function, L 1/2 of tau and y would just be half of the absolute value of tau minus y. So, this function is like piecewise linear, and the place at which the slope changes is exactly at the place where the sign of y minus tau changes, right? So if Q is 1/2, then the slope is either 1/2 or minus 1/2. Okay, it's like the absolute value function. And as you make the quantile you're aiming for more extreme, you just sort of kind of like tilt this absolute value function. And sort of the reason why it's called pinball loss is, you can maybe visualize this as like the trajectory of a pinball bouncing off something, or I guess any other kind of ball at your preference. Okay, does this make sense? Okay. Yeah, and sort of the fact that we're going to be interested in will sort of prove the qualitative version of this, which is just sort of like a one-liner in a moment. And I've got the proof of the quantitative version in the notes, but I think I'll skip over it in class time because it's kind of technical. Is the fact that pinball loss elicits quantiles. Okay, so if you minimize, okay, so there's going to be like two things here. The fact that pinball loss elicits quantiles is okay. Really, that's sort of corollary of the statement we're really going to care about, which is that if you minimize pinball loss over a distribution where the class of models you're minimizing over are just constant predictors, what you're going to get are the target quantile of the underlying distribution. But that's a corollary of what we're really interested in, which is the fact that if you give me a model and it fails to satisfy marginal quantile consistency, then what I can do, just as I did in the case of means, is I can shift that model, correct it so that it's no longer biased with respect to marginal quantile consistency, and that shift will only reduce the pinball loss. And it's like the sort of more interesting fact that we're really going to care about. Okay. All right, so let's write down the proof of sort of the simple version of this, and then I'll assert for you the statement of the sort of more quantitative version, but I won't make you suffer through it. Here's the simple version. For any continuous distribution, T, well, for any continuous distribution over label, and any target quantile lie in 0 and 1. If I say that tau q is the result of solving the minimization problem, where I'm minimizing overall thresholds tau, the expected pinball loss okay, so solving a regression problem where, okay, my model class is very simple, it's just constants. And my loss function is pinball loss. Okay, so when my loss function is pinball loss, this is sometimes referred to as quantile regression for reasons that will become clear when I write down the rest of the lemma. Then this quantity is a Q quantile of the distribution. Okay, so just as solving a squared error regression problem over a set of constant functions gives you the mean of a distribution, solving a pinball loss regression problem, or sometimes called a quantile regression problem, gives you a target quantile of the distribution. Okay, so possibly you've encountered this statement before, like for absolute value and medians, right? So just as sort of, if you're interested in the mean of a distribution, squared error regression is a good thing to do. If you're interested in a median of a distribution, absolute value regression is a good thing to do. And that statement generalizes, you know, for any quantile you might be interested in, there's some tilt of the absolute value function that will, you know, if you minimize that loss function, that tilted loss function, you'll get the target quantile. So this is pretty straightforward. This is going to follow from just sort of looking at the first order optimality conditions of the loss function. Okay. So now this is a convex function. Okay, and since we're assuming, oh yes.
Why is the argument taken over the interval from 0 to 1?
Oh, yeah, in general, it would be broader. I guess here I'm assuming the labels are between 0 and 1, but you're right. In general, the quantiles could live in, you know, some arbitrary range. Yeah, so maybe let's remove that from the lemma statement. Good. Other questions? Okay, so this is a convex function. You know, we conveniently assumed that all label distributions are continuous. So you know, it's even a continuous convex loss function. And so it's going to be minimized somewhere where there is a subderivative equal to 0. Okay, and so we're just gonna take the first order optimality conditions. We're gonna take the derivative of the loss function. We're gonna set it equal to 0 and see what that tells us. And I'm saying subderivative rather than derivative because it's yeah, not differentiable here. But okay. Now, if I take the derivative with respect to tau, the optimization variable of the expected loss, well, yeah, this is a piecewise linear function, so the distribution is continuous. So I just have to take the derivative of each of the pieces of a piecewise linear, piecewise constant derivative. This is just equal to the expected value of 1 minus q slope of the function when the label is realized as something less than tau, plus q when the label is realized as something greater than tau. Defining terms is just the expectation of the indicator, the label less than or equal to tau, is q, which is just probability that the label is less than or equal to tau minus q. And so the only place we can have a subderivative of 0, setting this term equal to 0, is if tau is set such that the probability that the label falls below that threshold tau is exactly equal to q. Is the definition of a Q quantile. Okay, so the function is essentially constructed so that the first order condition, it's saying that the first order condition for optimality of this loss function is the equation that identifies a Q quantile. Okay, makes sense. Okay. So that's interesting to know, but is not on its own like super useful in the sense that, well, first of all, we're talking about here just optimizing over constants. We're not talking about more complicated models, but in particular, this doesn't tell us how much higher the pinball loss is if our model was predicting something very, very far from target quantiles. Right? The nice thing about the statement that we had for squared error was not just this corollary that squared error was minimized at the mean of a distribution, but sort of this strong quantitative statement that sort of said, okay, well, if your statistical bias was sort of meaningfully different than 0, right? If your statistical bias was delta, no matter how complicated your model was, we're not assuming you have some constant model. If I just shift your whole model over by delta, then I will meaningfully reduce your squared error by delta squared. And for the kind of, feedback loop that we eventually envision, where, maybe I deploy a model, you point out a way in which it is obviously wrong, like it has large statistical bias on some subset of the data, and then I fix it. And the hope is that this process doesn't go on forever. The hope is that I sort of necessarily converge to either perfection or something indistinguishable from it. Relies on the fact that big mistakes, like big errors in my model, result in large decreases in the loss function. Because the loss function in this argument is going to serve as some potential function, right? Like the nice thing about squared error is it's positive, for example. It can't go below 0. So if it's starting at some fixed level, you just can't decrease it substantially that many times. Okay, like the argument wouldn't work if the loss went down, but only sort of infinitesimally. Then maybe this process really would never converge. And so that's like the quantitative version that is sort of missing at the moment from this statement. Okay, like we're not saying like we know that the loss is minimized at the target quantile, but like maybe it's like almost minimized at, you know, things that are very far from the target quantile. And that's what we'd like to establish is not the case if we want to make use of this in potential arguments the way that we are going to be able to make use of squared error when it comes to means. Okay, does that make sense? Good. So we'd like to be able to, so let's first talk about the kinds of models that will result from fixing observed, large observed failures to satisfy a marginal quantile consistency. Okay, these are models that, just like in our simple fixes for mean prediction models, are just going to shift the whole thing. Okay, so let's say that some model F, someone told us was great, isn't so great after all because it's got marginal quantile here. Alpha. And let's let delta, some real valued quantity, be the shift. Such that if I were to shift my model by delta, and have this new model of x plus delta, probability that this new model produces a prediction that exceeds the realized label is exactly Q. Okay, so this is a shift so that the new model doesn't have any quantile consistency error. And by the way, why does there even exist such a shift? Well, it's because we've assumed that the label distributions are continuous, right? Like in general, like quantiles are going to be consistently like a little bit more annoying than means for various reasons. Like means are nice and continuous. Means, you sort of shift, all of your predictions up by epsilon. The mean of your predictions has gone up by epsilon. For quantiles, that's not necessarily true, right? Like in particular, like if I have some annoying point mass, then the quantile of my threshold can like shift discontinuously upwards as I shift my threshold above that point mass, right? Like for extreme cases, like distributions that have all of their weight on a single point, like it doesn't even really make sense to talk about 50th percentile quantiles. Like everything is either below that point or above that point. Okay, but like under this assumption that the distributions we're working with are continuous, well, it is the case that as I continuously shift my predictions upward, the marginal quantile consistency error in particular will also continuously shift. Okay, so the fact that I'm making this assumption of continuity is sort of important for delta even to be defined here. This is something that doesn't come up for means. Okay, so we'll see a couple of ways in which quantiles are like meaningfully different than means. Okay, but assuming everything's continuous, this delta exists. And let's say, just as before, that f hat of x, I'll call my new model, is just the model after this shift. So, so just as before, someone gave me this model, they told me, it was perfect, but I looked at it, I said, it doesn't satisfy marginal quantile consistency. It has marginal quantile consistency error alpha, and then, I shift it by delta so that it doesn't anymore. What I'd like to be able to say is that what I'd like to be able to say is that the pinball loss has gone down substantially. Now, again, this is where quantiles are going to be like a little bit more annoying. I can't say that sort of without any other assumptions. And again, you can think about sort of distributions that place all of their mass on a single point as sort of extreme counterexamples for this kind of thing. And since I want a quantitative version of this lemma that's going to say the pinball loss goes down by a substantial amount, it's not going to be enough to just make like a qualitative assumption like continuity. Okay, I'm going to have to assume actually that sort of if I make teeny tiny adjustments to my predictions, it shouldn't change my quantile consistency error by huge amounts. Okay, so before stating the quantitative version of sort of this qualitative observation over here, I need to sort of define a further restriction that I need to put on the label distribution, which is not just continuity, but a quantitative version of it, Lipschitz continuity. Let's fix any distribution. D over labeled examples. Also fix let's say that the distribution rho Lipschitz if for all x, when I zoom in on the conditional label distribution induced by x, and I look at sort of the quantile value for any pair of thresholds, tau is the smaller one, and tau prime is the larger one. That when I look at sort of the quantile value of tau under labels drawn from the conditional label distribution d of x, okay, so that's just the probability of the label less than tau prime. Okay, so this is the quantile value of tau prime. And I compare that to the quantile value again under the conditional label distribution given x, tau. Okay, so tau prime is the bigger threshold, so it's, this is the bigger number. It's more likely that a label is less than tau prime than it is that a label is less than tau, because tau prime is bigger than tau. Okay, so this is a positive number, but it shouldn't be too positive. if this distribution is rho Lipschitz, then the requirement is that this be less than rho times tau prime minus tau. Okay, so Lipschitz continuity is sort of connecting how fast the quantile value of a threshold can change as a function of how much I move the threshold. Okay, for smaller values of rho, the less it can change. Okay. Means are sort of by definition like one Lipschitz continuous. If I shift some distribution by delta, the mean of that distribution changes by delta. Quantiles don't have that property, right? If I don't assume anything, you know, I can shift my threshold tau by some infinitesimally small amount, and the sort of quantile value can shoot up from 0% to 100%. And this kind of Lipschitz continuity that I'm going to want to talk about and assume for the next lemma is sort of forbidding that kind of behavior. Okay, the smaller a value of rho I assume, the more stringent this condition is, and it's sort of saying, the quantile can't change by too much if I shift the threshold by just a teeny tiny little amount. Okay. Now, of course, by making rho larger and larger, I can weaken this condition, but that's gonna show up in the quantitative versions of the lemma that we're interested in. Okay. Here's the lemma that I'm gonna state for you, but will not subject you to the proof, although it's all in the notes if you wanna read it yourself. Let's fix any rho Lipschitz data distribution B. Okay. And let's fix any model. F with marginal quantile consistency error alpha. And let's let f hat be the shifted model. Let's let f hat model f of x plus delta with delta chosen such that f hat of x satisfies marginal quantile consistency. For some target quantile. Okay. Then we know two things. The first, pinball loss measured at quantile Q of the new shifted model f hat. Well, if the original model satisfied, it had substantial quantile consistency error, and the distribution was Lipschitz continuous, then the new model will have non-trivially lower pinball loss. The new model will have pinball loss that is at most pinball loss of the original model minus alpha squared over 2 rho. Okay, so to the extent that the original model had larger quantile consistency error, the decrease in pinball loss will be larger, although it'll be sort of moderated by the Lipschitz parameter of the distribution. The distribution is close to being discontinuous. If rho is very large, then the decrease could be small. On the other hand, the decrease is going to be better behaved to the extent that quantiles behave more like means, to the extent that the distribution makes the relationship between the threshold and the actual quantile it corresponds to sort of increasingly continuous. On the other hand, it won't go down by too much. So if I look at the pinball loss of the original model, well, it's not going to be, that itself was not smaller than the pinball loss of the new model, plus delta, the actual magnitude of the shift, the absolute value of delta times alpha minus alpha squared over 2 rho. Okay, so for means, our lemma was an equality. We sort of said, okay, if you have marginal mean consistency error delta, okay, and you shift your model to fix it, there the magnitude of your shift was the same as your marginal mean consistency error delta. We said your squared loss is going to go down by exactly delta squared. Okay, so a tight upper and lower bound, like we just understood exactly how much it would decrease. Here we've got two inequalities that sort of sandwich the decrease. It's not exact, and it depends on assumptions about the distribution, but it says, at least if you think of rho as a constant, the pinball loss will decrease by a lot, but not too much. Okay. Makes sense. So this is sort of the quantile analog of this nice lemma we had for squared error last class. Questions about this? Yeah.
I have a question about the additional assumption we have here. Like, is that only specifically to the pinball loss, or is it just because we're working with quantized time?
Well, so the assumption.
On the continuous.
Yeah, so we have this definition of Lipschitz continuity, and the reason I wrote down that definition is because the assumption goes into this lemma, which of course is specifically about pinball loss.
So does there exist another function, another loss function for quantile regression if you don't need that assumption?
Oh, no, I don't think so. Yeah, so I think this is sort of a fundamental fact about the fact that sort of the CDF, the distribution, can sort of have arbitrarily large derivatives or even be discontinuous, which is sort of very different from like the mean of a distribution. Okay, so quantiles are going to be like, sort of fundamentally a little bit more annoying to work with than means. Yeah.
This might come out from the proof, or I'm sure it does, but can you give me some intuition for why the second and third terms in the bottom inequality can't be negative together?
Okay, so let's see. It's probably gonna come from, you're asking, if pinball loss decreases when I shift the model, so like pinball loss of f hat is smaller than the pinball loss of f. So it definitely can't be that the pinball loss of f is smaller than the pinball loss of f hat. So you want like assurances that the sum of these two terms aren't negative. That's a good thing to be worried about. And I'm going to guess that this is going to come out of staring at the definition of Lipschitz continuity. So let's see. So we've shifted our thresholds tau by some delta. And in doing so, we have changed the sort of quantile value of the threshold by alpha. Right, so delta is the delta is sort of the analog of tau prime minus tau. And alpha, so delta is sort of the shift on the right-hand side. And alpha here is the shift on the left-hand side. Right? That's the sort of the quantile consistency error that we've fixed. And so, squinting our eyes for a moment, this condition is kind of telling us that like alpha is less than or equal to rho times delta. And so, what is it? So like in the extreme case, if alpha was equal to rho times delta, then I guess this would kind of come out as
Delta minus.
let's see. Where isolate only one of the variables. So, suppose delta was equal to alpha over rho. Be like alpha squared over rho minus alpha squared over 2 rho. That kind of intuition. But I guess the point is, why is this term, but like, why can I even like relate these two terms that depend only on alpha and terms that depend on alpha and delta? Well, that's exactly because of the Lipschitz continuity condition. Delta is the magnitude in sort of threshold space of the shift, and alpha is the magnitude in quantile space. Does that make sense? Okay, good. Other questions? Okay. Good. So let's see. So far what we've been doing is we've sort of been building up sort of our understanding of consistency conditions we can put on the model and shifts to the model that will fix inconsistencies when we find inconsistencies in these conditions, and how that relates to sort of loss functions that we're ultimately going to treat as potential functions. So in the last 10 or 15 minutes of the class, let me sort of introduce one additional basic tool that is going to help us think about learning from data. So thus far, we have been speaking as if we have direct access to the underlying data distribution. Everything we've defined has been with respect to the underlying data distribution. When we defined statistical bias, marginal mean consistency error, marginal quantile consistency error, we wrote down expectations for the underlying data distribution. When we wrote down squared error, Breyer score, pinball loss, these were again defined as expectations over the underlying data distribution. Now, of course, in general, we do not have access to the underlying data distribution. What we are going to have access to is samples from that distribution. We're going to have like a data set, okay? And everything we've talked about so far, is defined over these data sets. As we said last class, we can treat data sets as distributions if we want. It's the uniform distribution over those data sets. But ultimately, since we don't want to overfit to our data sets, the thing we're interested in is not all of the quantities we've defined over the empirical distribution on the data set, but rather all of these consistency conditions as we've defined them over the true underlying data distribution, despite the fact that we do not have direct access to that thing. Okay, so what we're going to have to do is we're going to have to run our algorithms, do things like check and correct these consistency conditions on the empirical distribution defined by the data sets that we have, but we want some ability to lift the guarantees that we have from those empirical distributions over data sets to the true underlying distributions from which the data was drawn. Okay, and so there's some basic sort of tools for doing that, things that are sort of called concentration inequalities, and I just want to introduce you to some of the basic ones to give us a toolkit to be able to talk about these things. All right, and so let's maybe introduce the first one by sort of proving a very simple theorem that if we do everything we've talked about so far, let's say starting with means, and we identify that our model has some statistical bias on the empirical distribution for a data set that we've drawn, and we debias the model using that data set, then we will have also substantially debiased the model from on the distribution from which the data set was drawn, assuming our data set is like non-trivially. Let's fix a model F. Distribution D. Now, let's let regular D, the distribution is a fancy D, regular D will be n samples drawn IID, drawn independently, our data distribution. Again, I'll write that like this. Okay. Now suppose we debias our model on the empirical distribution defined by the data set, because that's all we can do. We don't have access to the underlying distribution. Let's let delta be the shift. Such that our debiased model, I'll call it f hat of x, it's just f of x plus delta, satisfies marginal mean consistency on the empirical data distribution on the data set. Okay, so this is easy. We just compute delta given the data we have and we shift the model. Then what we're also promised that with probability 1 minus delta, high probability, little delta is small. What's this probability taken over? Well, over the draw of our sample, over the draw of our data set, D. We can also say that f hat has marginal mean consistency error bias at most alpha on the underlying data distribution, where alpha is at most the square root of 2 times log of 2 over our high probability parameter delta over n. This is saying that there's 2 parameters here. So it's saying, you know, hey, if we have some sample and we just pretend the sample is correct and we debias our model exactly on the sample, then, you know, of course, I can't give you a deterministic statement about what is true on the underlying distribution, because it could be that I was extremely unlucky in drawing my sample. Like maybe the kind of thing I'm trying to do is estimate the mean of a possibly biased coin. Well, if I take 1,000 flips, it's possible that all 1,000 of them came up heads, even if the coin was fair, right? It's unlikely, but it's possible. So I can't, you know, if what I'm going to do is I'm going to estimate the bias of the coin to just be the sort of empirical average with which I've seen heads. Of course, I can't promise you something deterministically on the underlying data distribution. But what I can do is I can make a high probability guarantee. I can say with high probability, how high? Well, pick your favorite parameter, little delta, and I'll make you a promise that holds with probability 1 minus delta over the draw of your data. I'll promise you that, it's not that you're going to have zero bias. That's too much to ask for. You have zero bias on the data set, but maybe not the distribution. But that your bias will not be larger than, well, the square root of log of 1 over delta. Okay, so the more certain you want to be, the wider the error bars I'm going to have to talk to you about with respect to your bias on the underlying distribution. But the width of your error bar here, the width of your sort of uncertainty here, it's going to grow only with log of 1 over delta. And so if you want, you can ask for a very high certainty, very small delta. Okay. And it'll also tend to 0 with 1 over the square root of the number of samples you've seen. Okay, so this is sort of a common rate you'll see when you want to sort of estimate parameters of things from independent samples. Like if I flip n coins, the empirical average of those coin flips will tend to the true bias of the coin at a rate that looks like 1 over square root of n. Okay, and that's what we're seeing here. So it's saying, okay, like assuming I've got a lot of data, so the denominator here is very big, then I can just operate as if the at least with respect to this very simple task of correcting the statistical bias of a model, I can just operate as if the data set I have is the data distribution, and that'll work. Up to this small error, the guarantees will carry over to the underlying data distribution. Yeah. Okay. And how come this is true? Well, this is a simple application of a probabilistic tool called Hoeffding's inequality that is going to be very useful over and over again whenever you want to prove that some conditions that you have enforced to hold on a sample also hold on the underlying distribution. This being just the simplest example of such a condition. Okay, but this is sort of a workhorse inequality whenever you want to prove something about whether your model overfits to data or not. Called Hoeffding's inequality. And let me just state it here because many of you have probably seen this before, but like if you haven't, here's a really useful tool you should remember. Hoeffding's inequality, and this is sort of like an additive version of it's sometimes called a Chernoff bound. And it's sort of a general kind of theorem. Here's what it says. It says, suppose we've got a bunch of random variables, x1 through xn, that are all independent of one another. Not necessarily identically distributed, just independent. These are independent random variables. And they're bounded. What I know ahead of time, before I realize them, is that for each I, however xi turns out, it's going to be bounded between ai and bi. Okay, so it's okay if the bounds are different for each of the random variables. They can each be distributed differently. The important thing is the random variables are independent of one another, and they're bounded, and I know what the bounds are. Okay. And suppose what I'm interested in is something like their sum or their average, something like statistical bias. Okay, so let's let Sn denote the sum of these random variables. then what Hoeffding's inequality is going to tell me is it's going to tell me with high probability, the realized sum isn't going to deviate by too much from its expectation. In particular, for all magnitudes t that the deviation could take, when I look at the probability that the realization of this sum, Sm, differs from its expectation by more than t, well, this probability goes down exponentially fast in t. At most, 2 times the exponent of minus 2 t squared. And this is normalized by essentially the scale of the random variables. It's normalized by these terms a and b that bound the random variables. So it's normalized by the sum I equals 1 to n of sort of the square diameter of the random variables. For each random variable, I'm adding up here the largest value it could take minus the smallest value it could take squared. Okay. And so this is saying that sort of, at least when sort of the deviation gets large enough to dominate the scale term in the denominator, the probability that the sum of a bunch of independent random variables exceeds its expectation by more than t goes down exponentially fast in t. And this theorem is just a very simple application of Hoeffding's inequality. So to arrive at this theorem, all we're going to do is instantiate Hoeffding's inequality. We're just going to observe that what is delta? Well, delta, the bias of the model, just the average over all of the points in our data set of, well, the label minus the prediction that our model made for the label. So it's just the sum of a bunch of terms. Okay, each of which looks like y minus f of x, and in fact looks like y minus f of x over n. Okay. And a presumption in the theorem is that the data set was sampled IID from this distribution. So each of these terms is an independent random variable. In fact, they're all identically distributed, which wasn't even needed for Hoeffding's inequality. And they're bounded, right? What are the terms in this sum? Well, each one looks like 1 over n times y minus f of x. Well, y is at most, y is by assumption something between 0 and 1. F of x is something between 0 and 1. And so each term in the sum that we're interested in is upper bounded by 1 over n and lower bounded by negative 1 over n. The expectation of this sum is just the statistical bias of the model on the underlying distribution. Okay, and so we're interested, if we make sure that there's no statistical bias on the data set, well, what's the statistical bias on the underlying distribution? It's just the deviation between, this realized sum on the data set and its expectation. That's exactly what Hoeffding's inequality allows us to bound. Okay. These sensitivity terms in the denominator, they look like 1/n. Okay, so the square of them looks like 1/n squared. Now there's n of them that we're summing up, but n times 1/n squared is still 1/n. And so we get an n in the numerator. And this means that as the data set grows larger and larger, this bound is going to become tighter and tighter. This is exactly what we want. And when is t going to sort of dominate this n term? So t is squared. So it's when t exceeds something on the order of 1/√n. Okay. That's why you can just plug this quantity into Hoeffding's inequality and verify that the promise is that the deviation will occur with probability at most delta when t takes this value. And yeah, so it's the fact that t is squared in here that causes the error to go down at a rate of 1/√n. Okay. That I'll see you on Thursday.